Please enable screen sharing. Adokshajan, can you please switch on your camera?
Yes, ma'am.
Adokshajan, were you there in the class yesterday? Adokshajan, were you there in the class yesterday?
Ma'am, yeah, ma'am, I actually joined, but I wasn't able to hear. My speakers had an issue or something. I wasn't able to hear yesterday.
Oh, yeah, that's what I saw you present, but your speaker was not on. So that's what I kept asking you. But I think there was some issue on your side. So you couldn't hear, right?
Yes, ma'am.
So for quite some time you were there, but then after that, so now it's all fine.
Yes, ma'am.
Oh. So we'll start now. So children, yesterday we were doing the Yesterday we did this mainly the atomic size. So we did the atomic size and we understood how there is variation in atomic size, and we based on the graph different explanations why the atomic size decreases first, then the atomic size becomes almost same, and towards the end why the atomic size increases. So basically the atomic size you realized depends on the number of unpaired electrons. So as the initially the number of unpaired electrons increase, then the atomic size decreases. You saw that. And slowly towards the end, the atomic size again increases. In zinc, there are no unpaired electrons. So we talked about all that, and then we saw a special condition where you see that when you go from 3D to 4D, there is an increase in size, but from 4D to 5D, when you go, the size is almost the same. It does not change much. And that is because of lanthanoid contraction. Then we talked about ionization enthalpy. And ionization enthalpy is first, what is ionization enthalpy? The first ionization energy, the second one, and what exactly is the meaning of ionization enthalpy? All those things we learned. And what are the factors which affect the ionization energy? Okay, so what are the factors which affect the ionization energy? We talked about that. And then we saw the variation in trends. So what is the variation? Generally, it increases. The ionization energy should increase because the size decreases. But there are a lot of variations in the ionization energy. And then we talked about the variations, why the different ionization energies are different from what they are expected to be. So all those things we did. Now this is just uh, all ionization energies together. This is from the CBSE textbook. And you can see the one which is in the dark, that is the ionization energy, or that is the oxidation state, which is the most stable. So here we saw scandium has only one oxidation state, that is +3, because after leaving 3 electrons, acquires a stable configuration of argon. So it is only one oxidation state. Titanium can have 3, but +4 is the most stable oxidation state. Why? Because after losing 4 electrons, it acquires a more stable configuration. Then vanadium +5 is the most oxidation state. Similarly, chromium, this is the most stable, and then +3 is the most stable oxidation state. Why is +6 most stable? Because after losing 6 electrons, it acquires a configuration of argon, which is very stable. Similarly, for manganese, +7 is the most stable oxidation state. For iron, you can see the +2 and +3, they are the most stable oxidation state. And as you go from after 7, you see the number of oxidation states increases. From scandium to manganese, the number of oxidation states increase. And then the number of oxidation states decrease. Zinc also has only one stable oxidation state. Why? Because it has, after losing 2 electrons from the 4s shell, it has 3d10, which is a very stable configuration. So this is a general trend of oxidation states. Why do elements in group in transition elements show variable oxidation state? It is because the energies of 4s and 3d electrons is almost the same, and all these unpaired electrons in 3d and 4s can take part in bond formation. So that is why they have so many stable oxidation states. Now, there are a few questions here which are asked based on oxidation state. one important question which is asked is this one which I would like to discuss with you. That is Cr2 plus, right? Is a reducing agent. Chromium in its +2 oxidation state um, is a reducing agent, and manganese Mn3 plus is an oxidizing agent, uh, even when both have D4 configuration. Okay, so you have to explain why Cr2 plus and Mn3 plus both have D4 configuration, yet Cr2 plus behaves as a reducing agent and Mn3 plus behaves as a oxidizing agent. Now, first you should let us write the configuration of Cr2 plus and see what is the configuration. So how will you write? Cr is, you can see from here, 1, 2, 3, 4. So Cr is 24, right? So since it is 24, what will be the configuration of chromium? It will be argon, 4s1 and 3d5. Okay, why does it become 4s1 and 3d5? Because half-filled orbitals are very stable. Now this is chromium. If I want to make it Cr2 plus, that means what should I do? I should remove 2 electrons from here. So if I remove 2 electrons, what will remain? Ar, 1 electron from 4s and 1 from 3d will go. So 3d4. Now let us see what is manganese. Manganese is 1, 2, 3, 4, 5. So this is 25. So it is argon, 4s2 and 3d5. Now if it is argon 4s2, 3d5, then what will be Mn3 plus? Mn3 plus means I must remove 3 electrons. So what will remain? Argon, 2 from here and 1 from here. So it will also become 3d4. Now the question is that both have the same configuration, then why does chromium act as a reducing agent? But however, manganese in its +3 oxidation state acts as an oxidizing agent. So first you should understand what is a reducing agent and what is an oxidizing agent. So reducing, tell me, reduction, what is reduction? Who will tell me? Sanjay, what is reduction? Sanjay,
Ma'am,
what is reduction? What is reduction?
ma'am, in the sense from higher number to lower number.
Yeah. So reduction is from higher oxidation state to a lower oxidation state. So if reduction is from a higher oxidation state to a lower oxidation state, what is a reducing agent? Reducing agent is the one which should get oxidized, right? So what is oxidation? Oxidation is from a lower oxidation state to a higher oxidation state. So the question is, why chromium is a reducing agent? That means from Cr2 plus, why does it change into Cr3 plus? Okay, if it has to behave as a reducing agent, it should get oxidized, isn't it? So it should change into Cr3 plus. So if it changes into Cr3 plus, what will be the configuration now? It should become argon 3d3. All right. And in case of manganese, it should, if it is a good oxidizing agent, then what should happen? It should get reduced, right? So its oxidation state also should become Mn2 plus. From Mn3 plus, it should become Mn2 plus. What will be the configuration of Mn2 plus? It will be argon and 3d5. Right? Now in chromium and argon, 3d3 is very stable. Yesterday I told you what is the reason for extra stability for 3d3 in case of chromium. It is because the three the D shells, they split into two, and the three D shells with lower energy, they are half filled. So you can say because of half filled T2G, chromium 3 plus has a stable oxidation state. And manganese 2 plus, why does it become stable? Because of half-filled orbital. So in both cases, these are more stable oxidation states. So chromium always wants to be wants to change from 2 plus to 3 plus, and manganese wants to change from 3 plus to 2 plus. So it wants to increase its oxidation state. This one wants to decrease its oxidation state. So this acts as an oxidizing agent and this one acts as a reducing agent. So writing all the various electronic configurations, you have to explain. So write all of them and then say manganese acquires a stable electronic configuration by losing, by gaining an electron, and this one, this one manganese is getting reduced, and hence it acts as a good oxidizing agent, and chromium is getting oxidized, hence it acts as a good reducing agent. So these are the type of questions which are asked in for give reasons. Okay. Now another question, this is question number 1. Then another question which is asked is that Cr2O7 2 minus potassium dichromate has this ion. Let me write it on another page. So potassium dichromate K2Cr2O7 is a good oxidizing agent. Good oxidizing agent. How will you explain that it is a good oxidizing agent? Okay, so if it is a good oxidizing agent, that means it should get reduced, right? So first let us find what is the oxidation state of chromium in K2Cr2O7. So K2Cr2O7 oxidation state, I told you how to calculate oxidation state of Cr in K2Cr2O7. How will you calculate? Potassium is Hari Raghav, do you know how to calculate the oxidation state of chromium? If you don't know, then all of you please tell me, I will explain. Okay, so what is the, how do you do the oxidation state? Are you, Sanjay, do you know how to calculate? Do you remember?
Not really, ma'am.
Okay. And Hari Raghav, do you remember? Vishal? Because for answering these questions, we have to do this part. So if you are not thorough with this part, then I'll explain. Hari Raghav, are you there?
Ma'am, yes, ma'am, but I am not sure with the oxidation statement. Can you explain?
Okay, so I will explain to you how to calculate the oxidation state. Yes,
I think
tell me.
for oxygen it will be 2 plus or something. There will be a fixed oxidation state, and for K it will be plus 1 or something. If you add up
Right.
everything to 0, and so
Yes.
that will be X. Like that's something we have to do.
Very good, Adhokshajan, very good. So actually, you know, for oxidation state, you should know some oxidation states are fixed. So
Yes,
you should know what are those fixed oxidation states. So like first rule for oxidation state is that oxidation state of alkali metals, alkali metals, that is group 1 elements, is always plus 1. All alkali metals, it is plus 1. Then oxidation state of oxygen is minus 2. All right, it is minus 2. Then the third one is the oxidation state of hydrogen is plus 1, except when it is forming bond with metals, it is plus 1. Then the fourth is oxidation state of group 2 metals, right? It is equal to plus 2. And oxidation, sum of fifth rule is that sum of oxidation states, or sum of oxidation states of all elements in a compound is equal to 0. If I add up all the oxidation states, it should be equal to 0. And the last one is that oxidation state of pure element. Okay, the element by itself, it is always equal to 0. Okay, so K2Cr2O7, how will I do potassium? Potassium is in group 1. So 2 into plus 1, right? 2 into plus 1 plus chromium, I don't know. So 2x plus oxygen is how much? 7 into minus 2 is equal to 0, right? So 2 plus 2x minus 14 is equal to 0. So 2x is equal to 12. So x is equal to 6 plus 6, right? So what is the oxidation state of chromium? It is plus 6, right? So why does chromium act as a good oxidizing agent? So to become a good oxidizing agent, it should get reduced. So when chromium is in its highest oxidation state, it readily reduces to a to another oxidation state where chromium's oxidation state is plus 3. So from plus 6, because I told you, plus 3 is also a stable oxidation state. So when an element is in its highest oxidation state, it has a tendency to come down to a lower oxidation state if there is a possibility of a lower oxidation state. So chromium changes from plus 6 to plus 3 easily. Why? Because in the last slide I showed you, chromium has two stable oxidation states, one plus 6 and the other is plus 3. So from plus 6, it quickly uh, changes from plus 6 to plus 3, hence it gets reduced. And since it gets reduced, it acts as a good oxidizing agent. So elements, when they are in their higher oxidation states, they have a tendency to be good oxidizing agents because they can come back to a lower oxidation state. Similarly, there is another one which is a very good oxidizing agent, and that is, you must have heard, potassium permanganate. When we did oxidation reactions in organic chemistry, I showed you potassium permanganate is also a very good oxidizing agent. So what is potassium permanganate? KMnO4. Now, using the same technique, if I find out the oxidation state of manganese here, it is plus 1 plus x plus minus 2 into 4 is equal to 0. So x is equal to plus 7, right? So manganese is in its highest oxidation state. Now, from plus 7, what is the next stable oxidation state of manganese? The next stable oxidation state of manganese is plus 2. So it can go from 7 to 2 easily because 2 is also a stable oxidation state. So what happens to manganese? It gets reduced, and since it gets reduced, it acts as a oxidizing agent. Right? It acts as a oxidizing agent. So if it loses 5 electrons and changes to plus 2 oxidation state, and the electrons which it loses, they are gained by somebody else, and that one who gains the electrons gets oxidized, right? So it gets reduced. So potassium permanganate itself gets reduced, and hence it acts as a oxidizing agent. So this is what? This is reduction, and anything which gets reduced is a good oxidizing agent. Okay, so there can be simple questions like this, which you should be able to answer. So why potassium dichromate is a good oxidizing agent, why potassium permanganate is a good oxidizing agent, because they are in the element in the central, the transition element present in these compounds they are in their highest oxidation state. And since they are in their highest oxidation state, they cannot increase their oxidation state further, right? So they cannot act as a reducing agents. They can only act as a oxidizing agent. So they lose electrons and they get reduced, and no, they gain electrons and they get reduced, and hence they act as good oxidizing agents. So there are questions like this which you may have, which you may come across, which can be answered with the help of uh, this oxidation, and I mean with the help of oxidation number. Okay, so knowing the oxidation states of different elements. So 3-4 type of questions from oxidation states are asked. One is always, uh, why do transition elements show variable oxidation states? The reason is because the energy of electrons in d orbitals and 3d and 4s, they are almost same, and so all these electrons which are unpaired can participate in bond formation, and hence you will have multiple oxidation states. Uh, why manganese? The number of possible oxidation states is equal to the number of electrons in the S shell plus the number of unpaired electrons in the highest oxidation state will be what? Number of electrons in the S shell plus the number of unpaired electrons in the uh, D shell. So looking at that, you can write the various oxidation states. The next type of question is, which is the most stable oxidation state for each one of them? How will you figure out which is the most stable oxidation state? So you know the most stable oxidation state is the highest oxidation state in the first few. The most stable oxidation state is the highest oxidation state. Why? Because by losing this many electrons, the element acquires a stable configuration of the nearest inert gas, and that is argon. So like that, there are a few questions. I hope they give you a worksheet with all these give reason type of questions. So if possible, I will send it to them so that you can read through them and answer. Okay. So all these things which I have taught about oxidation state, I have put them together. So elements which give greatest number of oxidation state occurs in or near the middle of the series. So in any series, the elements which are in the middle of the series, they will have greatest number of oxidation state. Like in 3D series, manganese has the highest oxidation state. Manganese exhibits all oxidation states from +2 to +7. Then elements in the beginning of the series exhibit fewer oxidation states because they have small number of electrons which they lose and contribute to sharing. And elements at the end of the series show fewer oxidation states because they have too many electrons in the d orbitals. So they have few vacant orbitals which can be involved in bonding. So that is why when you go to the extreme right, the number of oxidation states decrease, because zinc has only one oxidation state, that is +2, because all the d orbitals are completely full and they do not take part in any bond formation. Then we did all these, this is for ionization energy. Now we have to do, next is this. All these things we have done. Okay, so now we are going to start something new and today, and that is also very, very important, and we have to understand it thoroughly, and that is trends in electrode potential. Now you need to understand, recall your electrochemistry properly, so then only you will be able to understand this electrode potential. So let me first remind you of what electrode potential is. Hmm? Okay, so we will just start there. This is. Electrode potential. So first let us recall what is electrode potential. So when we were doing electrode potential in electrochemistry, I told you that supposing I have um, a metal rod, any metal M, this is a metal M, and it is dipped in its own solution, which is a salt of that metal. So it has ions like Mn plus ions. Okay, you can understand it better like if I have zinc rod, right? And it is dipped in zinc sulfate solution, which will have Zn2 plus ions. Okay, so if I have a metal rod dipped in a solution, in its own solution, there are two possibilities. One possibility is that the metal, right, it will uh, lose electrons. It depends on the tendency of the metal. It may lose electrons and the electrons will lose electrons and and it will go into solution. Okay, so after some time, the zinc rod will reduce in mass and the number of zinc ions will increase. If that is happening, then what is the reaction? How can I write the reaction? I will write it as Zn, losing 2 electrons, Zn2 plus 2E minus. Okay, so what is happening here? This it is zinc is getting oxidized. Why is it getting oxidized? Because it is losing electrons. So I have also told you oil rig, right? So oxidation is loss. So what is happening here? Here it is oxidation. If I want to write a general reaction, can I write it? I can write it as M changing into M N plus Ne minus. Okay, so that is oxidation. It is getting oxidized. Now, because of this, what is happening is that on this rod, there will be excess of electrons. And here there will be a positive charge. So there will be a potential which will develop. And this potential which develops here is known as the electrode potential. Now, in this case, it is developing as a result of oxidation. So we will call it S, standard oxidation potential. Standard oxidation potential. We have learned all this in electrochemistry. I am just reminding you. Standard electrode potential, we write it as SOP, standard oxidation potential. Now, if there was a metal which was just the opposite, like if I had copper dipped in copper sulfate solution, so that if there was another metal here, right? And in this case, the metal rod was in such a way that it is dipped in its own solution. This is M, and this is Mn plus. Now this time M is copper, and this is copper sulfate solution, so that is copper 2 plus ions. Now copper has a reverse tendency. What it does is it steals electrons from the rod, and what it does, it gains electrons and changes into copper. So what is happening? The opposite happens here. So copper from the solution gets deposited on the surface of copper. The copper ions in the solution, they gain electrons. And so what happens? This rod becomes positive, right? And again, a potential develops. How will I write here? Cu2 plus 2E minus is changing into copper, right? So what is happening here? Oil rig reduction is gain. So it is what is happening here? Reduction. So the potential which develops here, that is called the SRP. What will be SRP? SRP is standard reduction potential. Standard reduction potential. Okay, so these are things which you should remember. Standard reduction potential. Now, when a metal is changing in, whenever a metal is changing from this solid to this state, it is the change that happens into the aqueous state. So basically what is happening, the metal is in its solid state here, right? When it is put in solution, here it is in solid state and here it is in aqueous state. Okay, so this change here, whatever the enthalpy change occurs here, is known as an delta H. Okay, so what I'm trying to explain to you is that let us look at this reaction. The reaction that we are going to look at is metal which is solid, right? We have to change it into metal which is aqueous. Metal ion which is aqueous, Mn plus 2E plus Ne minus. Right? Now for solid to change to this state, whatever total energy is required, that is called enthalpy, that is delta H. Now this delta H is not just, you can't calculate this delta is the energy which is required to convert the metal which is in solid state into the metal in which is aqueous ion. There are a lot of processes which happen in between to understand electrode potential. If you remember in class 9, or not 9, in class 11, you must have heard or done something called Born-Haber cycle. Have you done Born-Haber cycle? Any one of you remember? Adhokshajan, do you remember Born-Haber cycle? Adhokshajan, do you remember Born-Haber cycle? Vishal or Hari Raghav, Sanjay, anyone remembers Born-Haber cycle? Hari
Ma'am, I'm
Raghav,
aware,
are you?
ma'am, but I don't remember now.
Okay. So, so we are going to revise with you. See, so what happens is there are multiple steps which happen. Okay, so what are the multiple steps which occur? When metal which is solid, it has to change into metal ion which is aqueous. So many steps occur. So the first step is there is this metal has to lose electrons, isn't it? Now metals, what is ionization energy? Ionization energy is the energy which is required to remove an electron from an isolated gaseous atom. But here, what is the condition of my metal? My metal is in solid state. So what will I have to do first? If you see here in the bottom slide, if you see here, what do we have? Metal in this state. And we have to convert metal into, say, +2 oxidation state aqueous, right? So if we have to do this, then first we'll have to convert the metal into gaseous metal which is a gas. So for converting metal solid into gaseous, what is the energy which is required? The energy which is required is atomization energy. Okay. Now, after the metal is in its gaseous state, then I start removing the electrons. So I remove one electron. So the energy which is required to remove the first electron is my IE1, the first ionization energy. Then from this one, I will have to remove one more electron to make it in +2 oxidation state. So that will be IE2. So this is IE1 and this is IE2. So what will I have to do when I get a solid metal? First, I have to give it energy to change it into gaseous atoms. So it should, that depending on its metallic bonding, the energy which is required, the atomization energy I will have to change it into gaseous atom. Then from there, I will have to give again more energy to pull out one electron. Then again, some more energy to pull out another electron. So 2 electrons. And then what will happen is that my element will change like this. So that my metal will change into what? It will change into Mn2 plus ion. Now this Mn2 plus ion is in gaseous state, isn't it? Because first it was solid, then I heated it, it became a gas, and from the gaseous form I started removing electrons, so I got my metal ion, but it is in gaseous state. Now when I dissolve it in water, when it goes inside water, then what happens? Then this metal ion gets, because it is positively charged and water is also polar, then what happens? Water molecules surround this metal atom. So this is one water molecule, this oxygen is negative and this is positive, so there is some bond which is formed. Then another water molecule here, HOH. So there is some more bond is formed here. Then another water molecule here, HOH. So here also there is some bond which is formed. And then here also some bond is formed. And this water molecules, when they form the bond with some temporary bond or force of attraction occurs between the positively charged ion and water molecules, it releases some energy. And that energy which it releases, that is known as hydration energy. Okay, so it is this hydration energy which uh, the element releases, hydration energy, and then it changes. So the energy which is required to change the metal into metal aqueous ions, into M2 plus ions, that energy, total energy, is the sum of all these energies. Okay, so in addition to, that's what I have written here. In addition to ionization and enthalpy, other factors such as enthalpy of atomization and that and ionization enthalpy 1, then hydration enthalpy, etc., determine the stability of the particular oxidation state. So whether this oxidation state is stable or not will depend on the sum on this delta H. Okay, so more the higher the value of delta H, then or the more energy, which is if the value of delta H, the negative value of delta H is high, then the metal atom is very, very stable. So we have to understand this. So this depends on the sum of all these energies. So if I take the sum of all these energies, you see delta H. What is the delta H that we are looking at? That is the energy which is required to convert metal which is solid into M2 plus. We are taking a special case M2 plus, which is aqueous, plus 2E minus. So what is the delta H? This is the delta H that we are talking about. So this delta H will be the sum of atomization enthalpy plus all ionization enthalpies plus hydration enthalpy. Now the enthalpy of atomization we represent as delta AH. Then delta I H1, delta I H2, they are ionization enthalpies and they are all positive. Why are they positive? Anything that you give to the system is positive and anything that is released by the system is negative. Hydration energy is released always, it is given out, and this is the energy that we are giving. So these are endothermic and this one here is exothermic. So you can see here this is these are the endothermic enthalpies and these are exothermic. And the sum of all these will determine the delta H. And the value of delta H will determine the stability of the oxidation state, of a particular oxidation state. Whether that will be stable or not. And the stability of the oxidation state will tell us, we will understand the electrode potential, whether the electrode potential is high or low, or what is the trend in electrode potential, we will understand by understanding the values of delta H. Okay, so that is why We have to look at all these. So here the next important thing, so first important thing we understood is that the delta H value, which is the energy which is required to convert a metal into a aqueous metal ion or metal ion in its aqueous state, that delta H depends on so many factors. And we have to consider each factor to understand what is delta H. And when we understand delta H for the reaction, we will be able to understand the electrode potential. What is the electrode potential? Directly depends on delta H value. So if the negative value of delta H is high, then electrode potential will also be high. Now, when I say electrode potential, I always mean standard reduction potential. We always talk about electrode potential is always, when I say electrode potential, we don't talk about oxidation potential. We always talk about SRP. All the values which are given, they will be in terms of SRP. So if the negative value of delta H increases, the electrode potential also increases. And if the electrode potential is increasing, then the reducing nature of the metal also increases. Okay, because E0, if we have, if you remember in electrochemistry, we learned if E0 is positive, that means if the reduction potential is high, that means it can reduce easily, right? If the reduction potential is high, what does it mean? It means reduction can happen more easily. High reduction potential, copper has a high reduction potential, so it gets reduced easily. If the reduction potential is negative or it is less, that means it can be oxidized easily. So these are things which we have already learned in the past. So I'm just revising all these things to understand the trends in in this electrode potential or the trends in indirectly in reduction potential. Now let us take each all these trends. There is different trends are there, and what are the trends and how are the trends? This is the general trend in electrode potential. These are the trends. Trends in electrode potential. Please understand these questions are very easy if you understand them. If you try to memorize them, then they are very difficult. Now, if you see, this is 3D series. So in 3D series, if you see here, from the top to the bottom, if you see all the values which are given here, you can see I have taken this from your textbook only. So this is energy of atomization, first one. Then first ionization energy, the second ionization energy, this is hydration energy, and this is the electrode potential, right? So as you go from left to right, we have to see the trend in electrode potential. This is a graph. So the graph indicates that the trend is an irregular trend. When you go from left to right, the trend is irregular. We cannot say the electrode potential is generally electrode potential is increasing. We cannot say that always, but there is some irregularity, and each irregularity we will have to understand and figure out the reason for that. So what is the general trend? Let us first see what is the general trend. So general trend is general trend. So the first thing about the general trend is that when we go from left to right, right, the negative value of electrode E0, electrode potential E0 decreases. You can say negative value decreases. I'm saying in terms of negative value because the negative value is directly proportional to the value of delta H. Or you can also say the electrode potential E0 increases. right? If I say the negative value decreases, that means what is happening to the electrode potential? The electrode potential is increasing because the negative value is decreasing. Then there is, in many cases, the change is very mild. Change is mild, right? Why is there a mild change? You can see minus 0.28 here and then minus 0.25. The change is only 0.03. So sometimes the change is very mild. The maximum change is, of about only 0.5 from top to bottom. And what is the reason why the change is very mild? The change is very mild because as you go from left to right, what happens to the size? Generally, what happens to the size? The size decreases. So if the size decreases, what will happen? The ionization energy will decrease. Now see why I am saying all this is, you see there are two important parts of this delta H. One is this part, which is all positive, and one is this part, which is negative. So if both the parts are, if the positive is more, then the positive value will be more. If negative is more, then the negative value will be more. So if hydration energy is more, then the negative value will increase. If ionization energy is more, then the positive value will increase and negative value will decrease. So what will happen here? The ionization energy, when the size decreases, the ionization energy increases. So IE increases. As you go from left to right, generally IE, ionization energy, increases. Why? Because the size decreases. And the other thing which happens is that when the size decreases, the hydration enthalpy also, when it is a small size, the hydration enthalpy also increases. Okay, so keeping this in mind, we will look at different anomalies which are there in different places. Okay, so let us look at the first anomaly. Now, the first anomaly, I've already done all this so that it is easy for you. So first, you see here. So here you see when you go point, what is the general trend? From top to bottom, the negative value should decrease, right? So 0.163, then 1.18, it is decreasing. Then 0.90, again it is decreasing. But 0.90 to next one, it is increasing. So this is the first place where there is a difference in the trend. It is different from what is expected. Okay, so now what is the reason for this difference in trend? So the trend breaks here. So what is the reason? Manganese, where manganese breaks the trend. Now, why does manganese break the trend? It breaks the trend because negative value of ionization, electrode potential is increasing instead of decreasing. So what is the reason? The second ionization energy is less than expected. So if you see in manganese, the second ionization energy, see generally the second ionization energy, you see it is increasing from 1309 to 14 to 15, but 1592, it decreases here. So it is decreasing, decreasing. So since the ionization, why is second ionization energy decreasing? Because if I have Mn, if I want to make Mn2 plus, okay, Mn2 plus, what is the configuration? It is argon and 3d5. 4s2 is lost completely. So 3d5, which is a stable configuration. So it readily gives out one electron. So all these things are related. What we learned about the stability of a particular oxidation state, same way you have to understand. So Mn2 plus is a stable state. And so the second ionization energy is less. Now, if the ionization energy, which is a positive value, that decreases, then what will happen? The negative value will increase. So that is why. So because of stable D5 configuration, Mn plus to Mn2 plus. And that is why. So here this value, what is the total value of delta H depends on, or what is the electrode potential depend on. If this hydration energy is high and this side it is low, some of these three energies, if this is low, right? Anyway, anything, then this value will become more negative. So this again here, this negative value is more, and so I mean the positive value has decreased, so negative value is more, and so this value also is more. So this is one case number one. So this is case number one. Okay. Then what is the next case? The second case. Now, if you see the second case is let us take zinc. Okay, so for zinc, here the from here, if you see 0.25 and here it is 0.76. Again, it is increasing. Normally, it should decrease, but it is increasing. Okay, we will leave copper for some time because copper is a special case. But from nickel to zinc, the ionization energy, I mean the electrode potential should actually be decreasing, but here zinc it is increasing. Now, what is the reason for zinc to increase? This is, sorry, there is a spelling mistake, E. Okay, so zinc trend, why does the trend break? Negative value of uh, electrode potential is increasing instead of decreasing. Here it should decrease, but it is increasing. Now, what is the reason? The second ionization energy is less than expected. Again, just like manganese, because of the stable D10 configuration. Because what is Zn2 plus? Zn2 plus is Zn2 plus is what? Zn2 plus is argon and 3D10. So when it has a stable configuration, so from Zn plus to Zn2 plus, it will require very less energy to pull out one electron. So the ionization energy is less than expected, and so the negative value increases instead of decreasing. So you see here from 19 here the trend, the second ionization energy is not increasing, it is decreasing, and that is why the trend in zinc is like that. Now, the next thing which you have to see is the trend of nickel. Now, in case of nickel and cobalt, you see 0.28 and 0.25, right? The trend that way is correct because it is decreasing, but it is decreasing very little. You can say they are almost the same, or you can say the electrode potential of nickel is almost the same as electrode potential of cobalt, or it is more than expected. This value here, 0.25, should have been less than 0.25 because you see from 1.18 it has become 0.44. Then from 0.4 it has become 0.28, but from 0.28 it is only becoming 0.25. Why are these two values almost the same, or why has nickel higher electrode potential than expected? So the reason is hydration energy of nickel is more negative than expected. So this is why we should know the combination of various factors is what decides the electrode potential. So what is special in case of nickel? Nickel releases more energy when it changes from gaseous ion to an aqueous ion. So the hydration energy is more negative than it releases more hydration energy than expected. You see here that in cobalt and nickel, the hydration energy which is released is quite high, and that is why the negative value is high, and so the electrode potential is more than expected. So all these reasons one by one you have to remember. Okay. Now the next very important question is that That is in case of copper. So this question is always asked in 3D series. All the elements except copper has a negative, and they have negative reduction potentials. Okay, their electrode potentials are all negative, except for copper where the electrode potential is positive. Why does copper have a positive reduction potential? So that is, or why does in this whole series, why copper has the highest reduction potential? So what is the reason for that? If you have learned in the lower classes, you remember that copper cannot displace hydrogen because the reduction potential of copper is more than that of hydrogen. So now let us see, this is the order. Now the reason is copper, the value of E0 is positive. What is the reason? Now this is another anomaly. Second ionization energy is very high for copper. Second ionization energy is very high for copper. Why? Because from copper to copper, when you have copper, it is 4s1 and 3d10. Then from 4s1 to 3d10, you have to change into copper plus, that is 4s1 and 4s1 gone, now it is 3d10. So in Cu plus oxidation state, it is very, very stable because of 3D configuration. Now, if I want to remove one electron from 3D level, I will require a lot of energy. So my second ionization energy is very, very high, because to change it into 2 plus, I will have to use a lot of energy because I am pulling out an electron from a stable configuration. So this second ionization energy is very high. Now, what is the sum of, what is delta H? It is a sum of atomization energy plus first ionization energy plus second ionization energy and minus the hydration energy. So the positive energy for copper, the positive for copper E0 will also, so this positive part, this whole positive part is much higher. And that is why the E0 becomes positive. And reducing nature of copper is very less, and copper is unable to liberate hydrogen from dilute acid because it has a very high reduction potential. So because it has a high reduction potential, it has a very high tendency to get reduced. And so it lies below hydrogen because it has a positive value, and so it does not displace hydrogen from. So why does copper have very high value for electrode potential? It is only because of it having a very high uh, value of second ionization energy. And why is the second ionization energy very high? Because second ionization energy requires to pull an electron from 3D configuration. So these are all ways to explain all this. Now, all the possible questions which are there from reduction potential, I have explained. Now we will do some MCQs later, and that time you will have to learn to apply this. Now, another thing that you have to learn is to connect the reactivity of the metal, trends in reactivity of metals. So this is to see reactivity of these metals. How will you compare the reactivity of metals? So to compare the reactivity of the metals, what you have to do? Reactivity is directly proportional to tendency of losing electrons. Okay. So if something so if a metal loses electrons very easily, right, then it is more reactive. So tendency of directly proportional to the tendency of losing electron. It is also directly proportional to the reducing nature of the metal. And it is directly proportional to the negative value of E0. Okay, so if the negative value of E0 is high, then the reactivity of metals is more. Okay, so since I wanted to make it directly proportional, I have written negative value of E0. Or you can say the reactivity of the metal is inversely proportional to the electrode potential. So higher the electrode potential, less is the reactivity of the metal. Or you can remember it like this: copper is less reactive than sodium. Sodium is very reactive. How will you remember that? Sodium, if I put a piece of sodium in water, it immediately, causes a explosive reaction. It fizzes and it gives out hydrogen. If you put copper in water, will it have any reaction? No. We in fact put copper in water and we drink copper water. So higher the value of reduction potential, lesser will be the reactivity. Or you can say reactivity, the lower the value of reduction potential, more will be the reactivity. When the negative value of reduction potential increases, the reactivity of the metal increases, and or if the reduction potential is less or the electrode potential is less, the reactivity is more. And also, if the electrode potential is less, then the reducing nature of the metal is more. Okay, reducing nature means it acts it acts as the negative lower the reduction potential, more is the ability of the element to act as a reducing agent. Like sodium is a better reducing agent compared to a copper. Okay, so that is how you have to look at all these reactivity questions. Now we will, if you have understood all this, these are all things which I have taken a lot of time to explain slowly. So in case, oh, Sai Kalyan has come. How are you, Sai Kalyan? After a long time, you are having exams? What happened?
Yes, miss.
So what exam do you have tomorrow? No exam, right?
Tomorrow no exam, it's only I joined.
Okay, okay. So what chemistry is over?
Yes, miss. First exam is chemistry.
Oh, so what are the topics for chemistry exam?
Miss, solutions, electrochemistry, and
Hmm.
chemical kinetics,
Hmm.
and alkynes and arenes, alcohols, phenols, 5 lessons.
Oh, wow. So how did you do the chemistry paper? Was it good?
Yeah, it was kind of easy, miss. Good only.
Okay, I'm so happy to know that. Okay, great. Okay, so I didn't notice when you joined. Have you joined just now or have you joined some time back?
No, miss, I joined in the first exam.
Okay. Uh, so now based on this, we can, write the trends in reactivity. So as I told you, what does the reactivity depend on? It depends lower the value of electrode potential, more reactive will be the metal. So we can say, if I write that complete trend, titanium will be more reactive than vanadium, which will be more reactive than manganese, which will be more reactive than chromium, and then zinc, and then Fe, and then Co, and then nickel, and the least is copper. Okay, you can see, you can write this is minus 1.63. Vanadium is minus 1.18. Manganese is also 1.18. What is manganese? So it is almost the same. So this is minus 1.18. And then it is chromium, that is 0.91, and then it is zinc, that is minus 0.76, and then it is iron, that is minus 0.44, and then it is cobalt minus 0.28, and then it is nickel minus 0.25 minus, and the last comes copper because it is plus 0.34. So the reactivity directly depends on the the electrode potential. So lower the electrode potential, greater is the reactivity. Lower the electrode potential, greater will be the reactivity. Now we will look at the next property, and that is magnetic properties of uh, D block elements. Now, when we say magnetic properties, we look at the elements could be, we say they are either diamagnetic or paramagnetic. Okay, diamagnetic or paramagnetic. Diamagnetic are those which have all paired electrons. Paired electrons. And if it has unpaired electrons, then it is paramagnetic. So if it has unpaired electrons, then it is paramagnetic. Now the magnetic properties are measured in terms of Bohr magnetons. That is a unit which you say BM, right? And how do you measure BM? It is magnetic moment mu is equal to under root n into n plus 2. N into n plus 2, where n is equal to the number of unpaired electrons. Unpaired electrons. Okay. So the value of magnetic moment, the calculated value of magnetic moment is given here. So in different ions, what is the number of unpaired electrons? So scandium, D0, 0 unpaired electrons, so it is the magnetic moment is 0. Now if I take titanium, I'm looking at only because S shell is always full, and so we don't consider S, we have to look at the unpaired electrons in the D shell. So in titanium, you see unpaired electrons, in one unpaired electron in the D shell. So its magnetic moment, if you calculate, it will come to 1.73. Now, if I make different calculations, now number of electrons in D shell, as it increases up to 5, the number of in manganese, it is 5 unpaired electrons. And then after 5, the electrons start getting paired. And so the number of unpaired electrons reduces, and so the magnetic moment also reduces. Now, the interesting thing that you will notice here is that, if there is one unpaired electron, the magnetic moment is 1 point something. If it is 2, then it is 2 point something. If it is 3, then 3 point something. So if in the exam, they give you the magnetic moment and ask you to calculate the number of unpaired electrons without doing any calculation, you can say what is the number of unpaired electrons. So if it is value is 1.73, it is one unpaired electron. If it is 4.9, that means it is 4 unpaired electrons. So that is what you will find the number of, you can find out the number of unpaired electrons in a. So most of these, almost all the compounds which are transition elements, almost all of them have some, they are paramagnetic, and their magnetic moment can be calculated. Zinc is an exception. It has no unpaired electrons, so zinc has 0. It is diamagnetic. It is not paramagnetic at all. Scandium also, if it loses the only electron which is there in its D shell, it also does not show any magnetic moment. Otherwise, all others, they will have unpaired electrons. So magnetic properties, all the important things I have put together. Substances which contain unpaired electrons in their orbitals, they are paramagnetic. Paramagnetic substances are weakly attracted in the magnetic field. There are another type, ferromagnetic, which are strongly attracted in magnetic field, like in case of iron. Substances which do not contain any unpaired electron, they are called diamagnetic. Most transition elements are paramagnetic due to presence of unpaired electrons. Paramagnetic behavior increases with increase in number of unpaired electrons, and it is expressed in the terms of magnetic moment, and it is related to the number of unpaired electrons. And how do you write it? I will write it here. Mu is equal to under root n into n plus 2. Okay, it increases from scandium to chromium and then decreases because number of unpaired electrons also decrease. Okay. First they increase and then they decrease. The next thing about, we can quickly finish a little more. So the next thing about these transition elements is about their catalytic properties. Okay, so all these transition elements, they have the ability to uh, to uh, act as catalysts. So there are many transition elements which act as catalysts. I can give you a list of elements which act as catalysts, like, certain processes. I don't know whether you have learned now, in organic chemistry has been reduced drastically, but there is a process called Haber's process. Haber's process is a process which is used for preparation of ammonia, right? And in that process, the catalyst that you use is iron. Then similarly, there is a process called contact process. Contact process is for the preparation of sulfuric acid, right? And the catalyst that you use is vanadium pentoxide. So vanadium is a transition element. Then there is another process called Ostwald's process. Earlier, we used to learn all these processes in chemistry, but I don't know whether it is good or bad, but now you don't have to learn. So this is for the preparation of nitric acid, and the element that we use as catalyst is platinum. Then there is something called hydrogenation, where you have learned hydrogenation of alkenes. Okay, when you have to reduce the alkenes and make them into alkenes, then the element that you use for hydrogenation is nickel. So all these transition elements, they are very effective as catalysts. Now, what is the property of catalysts? You have learned that, the catalysts, what they do is they reduce what you call is the activation energy. If you remember, we have done this sort of graphs. Okay. So this is a graph. So where, supposing this is the energy of the reactant and this is the energy of the product. It could be like this. Okay. And now the reactant doesn't change into product directly. The reactants have to overcome this activation energy, right? So the reactants have to overcome the activation energy. This energy here, EA, is the activation energy. We have learned it in kinetics. So this activation energy, the reactants have to overcome. Now, if I add a catalyst, what is the effect of the catalyst? The catalyst reduces the activation energy. So the activation energy is here, it is reduced. And so the reaction, the products are formed more easily. So what does the catalyst do? It reduces the activation energy. So all these transition elements, they act as effective catalysts because they are able to reduce the activation energy. Why they are able to reduce the activation energy? Because of the vacant d orbitals which they have, they can form temporary bonds with the reactants and form a state or provide a site where the reaction will take place more easily. So all these things are written together here. Catalytic properties, presence of incomplete empty d orbitals. When there is a large surface area, variable oxidation states, ability to form complexes, all these elements can be used as catalysts. This activity is ascribed to their ability to adopt multiple oxidation state to form complexes. Okay, now let us understand what are complexes. So next thing is the next thing that we will learn, it is about the complexes. So all these transition elements, they have a ability to form complexes. What are complexes? Complexes are, say for example, uh, I form, you must have seen, I don't know whether you have used that in the lab. You must have seen that if I take copper sulfate solution and I add to it ammonium hydroxide, right? If I take copper sulfate and ammonium hydroxide, what will I get? I will get ammonium sulfate and copper hydroxide. Now, in this copper hydroxide, if I add more ammonium hydroxide, NH4OH, more NH4OH. So this was already there, ammonium sulfate, NH4 twice SO4. If I add excess, now this one is a pale blue precipitate, pale blue PPT. Now in this precipitate, if I add more ammonium hydroxide, it dissolves and it forms a deep blue solution. Why it forms a deep blue solution is because of formation of this compound which I represent like this, CuNH3 whole 4 tetramine copper sulfate. Right? This ion which I have written in square bracket here is a complex ion. And this salt which I got here is a complex salt. Okay. Now these compounds, the transition elements, because of their small size and vacant d orbitals, it can form complexes like this. It can form complexes of this type. There is another compound which I can show you. Here also I can probably explain. Hmm. So, so what happens is that, when copper sulfate is there, what is the oxidation state of copper? Copper is actually 29, right? And in Cu2 plus, what is here the configuration is argon, 4s1 and 3d9, 3d10, sorry, 3d10. Now Cu2 plus what will be the configuration? Argon, argon, 4s0 and 3d9. Okay, if I write it like this, here, this is the 3d orbital. 1, 2, 3, 4. This is 4s and this is 4p. Right? So this is 3D. It has already got 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this is 3D, this is 4s, and this is 4p. Now the energies of all these are similar, almost same. Okay, I am not saying same, they are similar. The energy of 4s is actually less than 3d. So then if I look at the energy of these orbitals, it is almost the same. So of similar energy level, there are 4 vacant d orbitals, right? And copper is of small size and it has 4 vacant d orbitals. So what happens? Copper provides these vacant d orbitals to form bonds. So the ammonia molecules, so ammonia molecules here, one ammonia here, one ammonia here, one ammonia, and here one ammonia. These 4 ammonia molecules, they approach copper and they say, we have got a pair of electrons. Will you form a bond? So a coordinate bond is formed here, right? And when it forms a coordinate bond here, the ion which is formed is a complex ion. So by losing 2 electrons, initially it formed a bond with sulfate, so copper sulfate. But the four vacant d orbitals which copper provided, ammonia also formed bond. So why these ammonia only? Because ammonia already has a pair of electrons. So these paired electrons, they come and form bonds, and the type of bond which is formed is a coordinate bond. And that's why these complexes are also known as coordinate compounds. So next chapter that we are going to learn is about these type of compounds called coordinate compounds. So D block elements, they readily form complexes. Why they form complexes or coordinate compounds? Because they have small size. Why do they have a small size? Because of high nuclear charge. So they have high nuclear charge, and because of that, and vacant d orbital. So the nucleus is able to attract more ligands, more species towards it, and it also gives them a vacant orbital, and that is why they can form bonds there. So these are complex salts. So since they can form complexes with compounds, temporary complexes, some permanent complexes, and that is why they act as very good catalysts. Okay, so we have done most of it. I will need one more class to finish this chapter on D block elements. So thank you for joining. Vishal, thank you for continuing till the end. Sai Kalyan, thank you for joining in spite of your exam. What do you have on Monday? Sai Kalyan, what do you have on Monday? Are you there? Sai Kalyan, are you there?
Yes, miss.
What do you have on Monday? What exam do you have on Monday?
The next exam is on Thursday only, miss.
Okay, Thursday. Okay.
In the middle, that's
Okay.
exam for married students.
Okay. So after this chapter is over, I am going to send the recording to the learning room. So go through it. There are a lot of things in this chapter which you should slowly understand. If you don't understand anything, then just let me know. I'll explain that part once again before we conclude. Okay. So thank you very much. See you on next Thursday. Okay. Bye.
Bye, miss.
Thank you, ma'am.